Hello, my name is Maria Paula Alfonso, and I'm going to talk about sun-absorbing properties of perforated composite panels of recycled rubber, fiberboard sawdust, and high-density polyethylene. Firstly, acoustic environment is increasingly taken as one of the key factors deciding living quality in rural areas, which are continuously persecuted by noises from various sources. Recycled natural or synthetic polymers, typically waste rubber, may find their novel uses in the production of acoustic materials for their good impedance properties. The construction includes a pegboard and a porous filler. Basically, the pegboard, usually with a quality visual surface appearance, works like a Helmholtz resonator. In a Helmholtz resonator noise silencer, the porous filler acts directly as a sound absorber, and the structure can consume sound energy at the true resonance effect. The resonance frequencies of a Helmholtz resonator depend on the thickness of the perforated plate, the perforation ratio of the plate, the size of the perforation, diameter of the holes, the volume of the cavity between the plate and the surface of the wall or ceiling. For the experimental part, the next materials were used: high-density fiberboard, fresh high-density polyethylene HDPE pallets, and recycled rubber granules. Acoustic samples fabrication. HDF sawdust, rubber granules, and HDPE pellets were fully blended at a reported mass ratio of 40, 18, and 42%, with 5% MAPE as a coupling agent based on the total weight. The mixture was pressed with a mold into composite panels at 185 degrees centigrade for 20 minutes under a pressure of 1 megapascal. The most of the acoustic test samples are 5 mm thick. Also, the samples were drilled with an electric drill with 1 at 6 mm diameter holes arranged uniformly in an homocentric pattern. This picture is the schematic diagram of a platen press with a derived sample dies. In that picture is observed the WRPC sample drill for acoustic absorption test of 3, 6, and 9%. Sound absorption testing was conducted with an impedance tube standard at incident sound frequencies from 63 to 6,300 Hz. Results and discussions. The panels had satisfactory mechanical restraints, guaranteeing the potential utilization of the panels in exposed acoustic applications. However, the non-perforated panels show low sound absorption capacity. That is why, compared to the use of acoustic applications, dense panels need a perforation treatment. From the test, it was determined that drilled panels with the same hole size were found to have little influence on the natural frequency with the perforation ratio. Larger holes brought lower natural frequency values at a mixed drilling rate too. On the other hand, as diameter increases, the value of the natural frequency decreases, which shows the sensitivity of the cavity depth and the natural frequency. This can provide a practical guide for building a resonant acoustic structure simply by adjusting the distance between the perforated WRPC panel and the rigid surface of a building wall or ceiling. Low frequencies range. Low frequencies can be more dangerous to human health than high frequencies. Residents are normally exposed in mixed noises from indefinite sources such as air conditioners, elevators, water pumps, and traffic. For the control of low frequency noise, it's of no practical meaning to create WRPC panels at high perforation ratios. However, this can never negate the good performance of higher perforation rate in high frequency domain. Conclusions. Its sound absorbing performance is affected by three structural parameters: perforation ratio, hole size, and cavity depth. Cavity depth plays a more important role than perforation ratio and size. Large samples were for low frequency acoustic testing and small samples for high frequency testing. Perforated WRPC panels have broad bandwidth sound, but they show superiority in the low frequency domain below 1000 Hz.